Okay, so let me recapitulate what we did last time. So what we said was that well, if omega was a domain and A was a mid-edge in the boundary of omega, we defined Fz, which was equal to, well, the sum over all self-avoiding paths from A to Z that remain in the domain. Over x to the power of the length of the path times exponential minus I sigma times the winding number, the total winding number of the path. So we call this Fz. And what we had seen was that if you took, well, the sum over B was equal to 1 by convention. So if you took then the sum over the mid-edge in the boundary of this thing, then you would get 0. Okay, so what we did first was to prove this kind of locally and then sum over all the vertices to get this identity. And another way to write this identity, so this was if x is equal to xc, which is 1 over mu, with mu is equal to square root of 2 plus square root of 2. Okay, and sigma is equal to 5 over 8. Okay, so in particular, another way to write this was that the sum over B in omega minus A, B minus VB, FB is equal to 1 if you multiply it by 2. Okay, just because the contribution of A is exactly minus 1/2. So if you put it there, this is what you get. Okay, and maybe I will put the 2 inside because this here is a complex number of modulus 1. Okay, the length of the mid-edge, the length of the half-edge is 1/2. Okay, so any question about this? So now the idea is to look at kind of trapezoid domain like this. So, well, the domain is constructed like that. So you consider basically 2L plus 1 half edges, which are symmetrically disposed around A. Yeah, then you put a certain number of rank, so maybe T minus 1 ranks of hexagonal cells, and in a way so that each rank is larger than the other. And then you end up with blue edges. And yeah, you make sure to include these things, okay, so that you don't have edges that would point in this direction. Okay, you want basically to only have 4 directions for the outgoing half edges. Okay, and this domain is what we call STL. Okay, and just to, I mean, it's not really important where you put this guy, but I just take A equal to 1/2 to fix IDs. Okay. If you consider the translation of this, the reasoning would work the same. Okay. So basically, I want to use this identity to get me something about sums where I don't have winding numbers. Okay, because in the end, this is not what we are interested in, really, the generating function of the number of self-avoiding paths starting from a point with a given x. Okay, so let us define, okay, so I will call this side here alpha. This will be epsilon. This will be epsilon bar. And this will be beta. Okay? And now I call ATL. So if you want ATLX. Okay, just ATL. From now on, x will be equal to xc. Okay, all the time. So I call ATL to be just the sum over B in the boundary, okay, B in alpha minus A of x of sorry. X to the L. Gamma, okay, and okay, let me. So ATL is just a set of paths that from A go back, end up in a half edge, which is over there. Okay, we end up in a mid edge, which is on the segment alpha. Okay, but which is not A. Okay, when I say which is not A, I mean that I'm not considering the trivial path of length 0. Now BTL is, well, just the sum over A to beta XL gamma. Okay, I always consider gamma included in my domain. And finally, I consider ETL, which is the sum over gamma from A to epsilon union epsilon bar of gamma STN. Okay, so if I take the sum of these three things, basically, well, I'm just counting I'm just summing x to the L gamma for all the paths that start from A and end up somewhere on the boundary of the box, which is not A. Okay, and the first important thing we are going to see today, which is kind of just a reformulation of this, it is that C alpha ATL plus, so for x equal xc, plus BTL plus C beta ETL is equal to 1. Okay, and I'm going to use this, and I forgot to say, but this, okay, this is 2 VB minus VA minus A, in fact. And this is equal to 1 only if A is located on the left of the box, if you want. Okay, but it's a case in our case, so we have no problem. Okay, so of course, because this is equal to 1 in our case, what we have to show is that this sum here is equal to these three things. Okay, and I forgot to say, okay, this is C epsilon, and the important thing here about the constants C alpha and C epsilon is that they are positive. So what are their values? Cos 3 pi over 8, and C epsilon is equal to cos pi over 4. Okay, so what's the natural thing to do? What we want to show is that here, if you sum over B in beta, you get BTL. If you sum over B in alpha minus A, you get C alpha ATL. And if you sum over epsilon union epsilon bar, you get C epsilon ETL. Okay, that's so. Okay, so let's start with the case of let's start with the case of B. I'll write it like this. So okay, we are looking at the sum over B in beta of 2 B minus VB F of B. Okay, so, well, so this is equal to, well, the sum over B in beta of F of B, because this is equal to 1. Okay. So this is equal to the sum over, well, so from gamma from A to beta. What I mean here is really, well, that end up somewhere in this set. Okay, because I'm taking the sum over B in beta from the sum of the paths from A to B. And then I get x to the L gamma exponential minus I sigma W A B, no, W, sorry, gamma A B. But now, if you look at a path from alpha to beta, the winding number has to be 0. Okay? Every turn you make, you have to compensate it in order to exit here. And this is because it's non-crossing. Okay, so for in the other cases, yeah, what we have to figure out is, well, the value of B minus VB and the value of the winding numbers. Okay, so let's start with A. Okay, let me call this part, okay, alpha plus, if you want. Okay, and what I want to say is that first, okay, if you consider a path from A to alpha plus. And if you symmetrize it, then you get a path from A to alpha minus. Okay, and this relation is clearly bijective. When you do so, you don't change the value of this thing. Okay, and it remains equal to -1. But you change the winding number when you symmetrize. You change the winding number from this opposite. You change the winding number to the opposite value, to the conjugate, to the opposite value. So you change the value as a result. You change the value of this thing. You transform it into its conjugate. So for this reason, what you have is that, a path and its conjugate, a path and its symmetries, they have a conjugate contribution. So for this reason, what you have is that, okay, so by symmetry, okay, you have that the sum over A in alpha minus A of B, alpha minus A of, that's B minus VB f of B, it is equal to, well, minus the sum of B in alpha minus A of f of B. And it's equal to minus twice the real part of the sum over B in alpha plus of f of B. Okay? I mean, this is equal to the sum over B in alpha plus the sum over B in alpha minus, okay, with my definition. But we know that the two brings conjugate contribution. So in the end, you only get the real part twice. Okay. So now what can we say about this? So well, it's equal to, the sum over gamma from A to alpha plus of x to the L gamma. And what you have in afterwards is exponential I sigma times the winding numbers, but we know that W gamma A, B is equal to minus pi if B belongs to alpha plus, is equal to pi if B is in alpha plus. Okay, here you're really turning in the trigonometric sense of an amount pi. So this is the same for everything, so you can put it into factor, and you get exponential minus I sigma pi. Okay? So what you get overall is that this sum over B in alpha minus A, B minus VB, f of of b. Okay, so it's equal to minus 2 cos of 5 pi over 8. Okay, if you want minus 5 pi over 8, but this is not really important. This is where I take the real part. And then I get sum over gamma from a to alpha plus of x to the L gamma. Okay, and now what I can do is say that the number, well, this sum over alpha plus or this sum over alpha minus, it's the same. So I can just delete the 2 here and take, well, alpha plus union alpha minus, which is exactly what I wanted. Okay, and say that this thing, this is just cosine 3 pi over 8. Okay, because this thing is just cosine 5 pi over 8, and, well, cos x is equal to cos pi minus x. Okay, so we are lucky. This is larger than pi over 2, so this is negative, and the minus makes it positive. Okay, and for E, it's a bit of the same story. So let me, so any question on this computation so far? Okay, so. For E. So for the same reason, I have that. The sum, the same symmetry reason, I have that the sum over B in epsilon union epsilon bar of VB, B minus VB, FB, well, it's equal to 2 times the real part of the sum over B in epsilon B minus VB, f of B. And okay. Here you have to put 2. Okay, and the reason is that now, okay, the f of B is just, it gives you the, if you take a pass and you look at its contribution, okay, the symmetric gives you the conjugate contribution, and also the term B minus VB, okay, in one case it's J, and in the other case it's J square, which is also J bar. Okay, so everything is getting transformed by its conjugate, is getting mapped to its conjugate, so in the end you get something real. Okay, just erase this. Okay, so now this thing is equal to sum over gamma from A to epsilon. Of course, I'm summing over paths that remain in the domain. X to the L gamma. And then I have to multiply by J because of this. And the winding numbers, so if gamma is from A to epsilon, then the winding number of gamma A to B is equal to, it's equal to, let's see, yeah, I guess it's equal to 2 pi over 3. Yes, because you just have to turn twice basically to get it's equal. Yeah, you just have to turn twice to get there. Okay, so here we get exponential minus sigma I 2 pi over 3. Okay, so therefore, what we get is that the sum over B in epsilon union epsilon bar of B minus VB f of B, it's equal to 2 times the sum over B in epsilon of x to the of gamma from A to epsilon of L lambda, and then I have to multiply by cos 2 pi over 3 times, I guess, 1 minus sigma. Okay, so I can do the same thing as before. So these two, I can cancel it if I just sum over paths ending up here and there. Okay. And this cos, I think this is just, this thing is just 3 over 8. Okay, so 3 over 8 times 2 over 3 is equal to 1 over 4, I think. Everybody's okay with that. Okay, so this kind of concludes everything we had to squeeze out from the parafermionic observable, this complex things which is defined in terms of the winding numbers. And yeah, now we have, okay, some things that kind of looks like generating functions we want, but except that we have paths that are restricted to a domain. So yeah, we have to figure out what to do. What we are going to do is first send L to infinity. This will be kind of an easy part to get another identity. And then try to see what we can do with T in order to conclude. Okay, so everybody agrees with that? And we can move on. So this thing of this domain, it's just, okay, taking something symmetric, basically you're kind of sure to make all these complex quantities real, because symmetric paths will give conjugate, pairs of symmetric paths will give conjugate contributions. Yeah, it turns out that with this specific choice, you get thumbs with positive prefactors, and this is something which will have a crucial role in the remainder of the proof. Okay. So now let us make a few remarks. So what you can see is that when you increase L and T is fixed, what you're doing is you are enlarging the domain. So for this reason, you just get more path that goes from A to alpha, okay, if L is larger. Okay, I mean, alpha is alpha of L if you want. But, and the same is true for beta. Okay, I mean, for E, it's different because when you change L, you're changing the set of endpoints, and so you're really completely changing the set of paths you're considering. But for these sums A and B, you are just increasing the set of paths on which you're summing. Okay, and X is positive. You're summing positive stuff. So what you have is that for T fixed, ATL and BTL are increasing quantities. Okay, so they are bounded from above by 1 and 1 over C alpha, respectively. So I can call AT the limiting quantity, and similarly, BT. And these things are finite. Okay, so this is already something non-trivial because this AT and BT, they are sums of over path which, just remain between two planes, okay, and exit on either on the left or on the right. Okay, so there are some over infinite sets, but you know that they are finite just because you have proved this identity. Well, a consequence of this is that ETL is decreasing. Okay, the sum of the three things is constant. Okay, all the coefficients I have are positive. So from star, ETL is, well, okay, decreasing. When I say decreasing, yeah, I mean decreasing. Okay, I could say non-increasing, but it's okay. So then, okay, it's not a really important part, but let me suppose for a moment that the limit when L goes to infinity of ETL is equal to 0. Sorry, that the limit of this is positive. So, okay. So maybe I should tell you what we are doing now. So what we want to do now, okay, so if you remember, we had defined Zx as the sum of Cn x to the n over n larger than 0. Okay, so this was, Cn was the number of self-avoiding walk starting from the mid-edge A. So well, this is just the sum over gamma from A to H. Okay, remember that H is just the set of all mid-edges of X to the L gamma. Okay, and what we want to show is that our first task will be to show that this is infinity. Okay, so let's prove this using this identity. So they are basically, we are going to do it in 2 steps, and the first step is quite short. So if the limit when L goes to infinity of ETL is positive, then what you have is that ZXC, well, it is larger than the sum over T larger than 0, or larger than 1, yes, of ETL, of ET, sorry. So this is equal to infinity. Okay, I mean, the set of all paths, I mean, ET, okay, let's see. Yes. Okay, what's the matter here? Let's see. Oh, no, sorry. Okay, because here I'm just counting disjoint path. Okay, like for each values of L, I'm ending at different points, so I'm not counting paths twice. Okay, so from now on, we are going to assume that ET is equal to 0. Okay, and maybe it when we end up the proof, you might wonder, well, whether this occurs or this occurs. Actually, once you've proved what the connective constant is, you can actually prove that this decays exponentially fast, if you want. Okay, so there is no, this is this is a step of the proof. It's kind of, it's not necessary, but it makes things cleaner. But it's not that we don't know what happens. Okay, between these 2 issues, we know that this is true. Okay, so from this, what we get is that C alpha AT plus BT is equal to 1. Okay, we just take the limit in this identity. Now the thing is, what we have is that AT is an increasing sequence in T, and BT is a decreasing sequence in T. So AT will, so basically, the problem is that for AT and AT plus 1, you're going to count the same path. So the fact that AT does not converge to 0 will not help you to prove that ZX is infinite. So the bound you will get for ZX will be the sum of the BTs. Okay, and the BTs are the ones that are decreasing. So what we are going to show is that, well, BT may go to 0, but it cannot go to 0 too fast. Okay, so what we are going to prove that the sum of the BT is infinite using this identity and a bit more. Okay. So our first point will be to look at the difference between AT plus 1 and AT. okay, and t is larger than 1. So, okay. I have to do a drawing. So now you have these two infinite half planes. Maybe it's not really important what they are. Yeah, what's important is that here, okay. Okay, my distance is 3t plus 1 over 2. Okay, so if I have a path which is there, so maybe I should put if I have a path which is in AT plus 1 and not in AT, well, it has to enter this set of edges before going back to alpha. Okay, because if not, it would be in AT. Okay, because all the other edges, I mean, these are like the edges, I mean, these would be the mid-edges corresponding to AT. Okay, so if they stay there, basically, they have been counted. Okay, and if they go over there, well, they have to do something like this. Okay, maybe they stay a little bit, but I mean they can do it several times, okay? But yeah, at some point, yeah. So they have to touch basically a vertex here. Okay, so we look now at the path from the first vertex you see here. Okay, so you start from A, you stop at the first vertex you visit on the side, like beta t plus 1 if you want. And now you can say the following. If I'm just adding what I can say, I can decompose this thing into, well, a path going there and ending up there, okay, just adding this half edge. And another path, which is going from there. Okay, let's just follow it to there. Okay, so what I'm drawing here are just two things that kind of look like path in BT plus 1. Okay? And in fact, if you give me two paths in BT plus 1, I can reconstruct this path. Okay? Okay, if you shift, if you give me two paths of BT plus 1, meaning you give me the green thing, and you give me the red thing but shift it there, well, I know where to place the red thing in order to have my construction. So yeah, if you give me two like bridges of size t plus 1, okay, I can reconstruct my thing. And of course, it's not true. I mean, there are pairs of bridges that would give me crossing stuff, okay? So I mean, this would give me a self-avoiding path only if the red path doesn't cross the green path. Okay, but basically, if I'm counting pair of bridges, I'm kind of over-counting this path. So what I have is that this thing, okay, which is the sum of the over these orange paths of x to the length, it is smaller, okay, than the number of pair of bridges. So what I would get is, well, bt plus 1 square. And if I take the total length of this pair of bridges, it's actually the length of the pair of path, the length of the orange path plus 1, because I have added 2 half edges. So here, when I'm taking this square, okay, I'm summing over a pair of bridges, but I'm taking x to a length which is what I need plus 1. So I need to divide by x here. Okay, do you agree with this? Okay. If you have a path that contributes to 80 plus 1 without contributing to 80, basically, you can encode it by taking 2 bridges, okay? And when you sum over this path x to the length, basically it's the same as summing over a pair of bridges x to the sum of the lengths minus 1. And this sum over the pair of the 2 bridges is exactly 1 over xc bt plus 1 square. And here we are overcounting because we are contributing pair of bridges. We are summing also pair of bridges that do not correspond to an orange path. Okay? So now that you have this kind of relation, basically, you want to inject this in there in order to get some kind of discrete differential equation on BT. Okay, so if you take star t plus 1 minus star t, what you get is C alpha AT plus 1 minus AT plus BT plus 1 minus BT is equal to 1. Okay, so what you get is equal to 0, sorry. So what you get is that 0, so we get bt plus 1 square over xc plus bt plus 1 minus bt is larger than 0. And here you need C alpha here. Okay, and 1 over xc, it's mu, so let me put mu here. Okay, so this is the identity we have. Okay, and now actually we can replace this by something else. Okay, so okay, you can either work with this directly to get an inequality on BT, or you can twist it a little bit to make your life easier. So what you have is that BT plus 1, it is smaller than BT. Why? Well, this is because AT plus 1 is larger than AT. Okay, and because of this identity, so this is what I called star T, I guess. So because of this identity, because AT is increasing, BT has to be decreasing. So here, this I can replace it by mu C alpha bt plus 1 minus bt plus bt plus 1 minus bt is larger than 0. Why do I like this? This is because what I get is that what I get from this, you can rewrite this as follows. So you get B bt minus bt plus 1 over, okay, bt minus bt plus 1 over, okay, let me check if I got my inequalities right. Okay, so this is true. I think everything is true. Over bt plus 1. Okay, let me check this. Let me check my notes just for a moment. Okay, so this is equivalent to this, I guess. Mu C alpha. And, okay, so yes, okay. This is where I got it. Let's see. Let's check. No, I'm just dividing by things that are positive. So here I get an inequality in this direction. Okay, and this thing, it's 1 over bt plus 1 minus 1 over bt. Yes, it's smaller. Okay, so I know that this is positive, and I know that this is smaller than mu C alpha. Okay, so what this gives me is that 1 over bt, it's smaller than 1 over b1 plus t minus 1 times mu C alpha. Mu C alpha, yes. You want a lower bound on bt, so you want an upper bound on 1 over bt. Okay, and yeah, if you look at this, like what you have is that the differential of bt is larger than the square. Okay, here you have a t plus 1, but it's not. So it really looks like, you know, the differential equation f prime is larger than f square, and the solution of this is 1 over x. In the discrete case, you have to replace this by bt plus 1, and this is a little trick here. Okay, so in particular, sum over bt is equal to infinity. Okay, when you take the inverse of this, you get something like 1 over t. Okay, so you get a sum that blows up. I mean, not by much, but it blows up. Okay, so if you remember, what this proves is that actually mu is okay. Well, the problem is that I've defined mu. Okay, so that if mu is a connected constant, this tells you that mu is smaller than square root of 2 plus square root of 2. Okay, and we still have to show the opposite direction. And for this, we have to show something for zx for x smaller than xc. Okay, so we have to show that. The second part is to show that if x is smaller than xc, then zx is finite. Okay, so everything is clear on this bound. Okay, so basically we were using this identity. Okay, we were using this identity in order to prove that that BT, and this identity and a relation between AT and BT in order to prove that, well, BT cannot go to 0 too fast. Basically, if we didn't prove that ET was equal to 0, okay, I mean, here you would just have 1 minus ET. I'm not sure it changes things by much, but okay, this was better to do it this way. Okay, so now let us try to prove this. And well, we are still going to use this, but in a very weak manner. What we have from this is that BT is smaller than 1. Okay, so what we have is that BT of XC is smaller than 1. So now if you take a version of BT, but for a smaller x, okay, well, this is equal to, well, the sum from gamma from A to beta, when now beta is just, like infinity in this direction, of x to the L gamma. And, well, you can just say that this is equal to, it's equal to this thing. You can write it as x over xc to the L gamma times xc to the L gamma. Okay, and now you can say, oh, well, L gamma, it has to be larger than 2t. Okay, the shortest path that can cross this, they are I mean, I have to use 2t edges. Okay, I mean, I have to use at least t, but it's also true that I have to use at least 2t. So therefore, this is smaller. Okay, so this is larger than 2t. X is smaller than xc, so this is smaller than 1. So I just here replace this by 2t. I get an inequality, and I get that this is smaller than x over xc to the 2t times b to the btxc, which is equal to, which is smaller than 1. Okay, so now I have that for x smaller than xc, bt x decays exponentially. Okay, and the idea now is to control zx with bt, okay, saying that basically if bt is, if the sum of over t of bt is summable, then zx is finite. Okay, and the idea, okay, we will just take a small break and then prove this, but the idea is very similar to this one, only just more complicated. When you try to write these generating functions, basically, you can do some path decomposition and control the generating function of one thing by the generating function of some other stuff. So the first thing we did that was to show that at plus 1 minus at was larger than bt plus 1 square. And the idea was that, well, the orange walks, you could decompose it into 2 bridges. Okay, so now what we are going to show is that basically, if you have a self-avoiding walk, you can decompose it in terms of bridges, and this bridge decomposition will help you to bound zx in terms of the bt's. Okay, so let's take 5 minutes of break, and we do this just after. So let's go back and try to prove a bound on Z using the fact that btx decays exponentially in T. So I will just use a first step. So first thing I will do is define some other function, which is hx, which is equal to the sum from A to, from A to H of L to the gamma, of X to the gamma L gamma, sorry. But here, I want gamma to be, somehow included in H plus. So what I mean by this is that I want to restrict two walks that never come back to this part. So all the walk will be located to the right of A. So it's a smaller sum than the X. But what I want to show is that actually you can control the X by Hx. So if you show that Hx is finite, this is sufficient. So why is it so? So let's try to make the computation. So in the X, you have several things. So well, first, here I'm in Hx, I will not consider walks of length 0. So this is just not a walk in Hx, just by definition. So in Dx, you have the walk of length 0. I say that C0 was equal to 1, so I just put this. This is. In Zx, I have also all the walks in that remains in the half plane. And now I have also other walks. There are walks that visit this green region. And these walks, I have several ones of them, so I will see what kind of cases I have. So what I can have is I have a walk that, never goes strictly to the left of A. So if I have a walk that never goes strictly to the left of A, it means that it just ends up somewhere here. And if I'm summing over all these walks x to the L to the gamma, then it means, and if I never go strictly to the left, this means that the first step has to be to the right, so the contribution this will give me, I can just delete, if I delete the last step, and I know, the last step is here. If I delete the last step and I know that I end up here, I have only one choice that will put me on the vertical of A, given the last step. So if I count all the walk going up there, basically I will be counting the same thing. And this is smaller. This sum is smaller than Hx. And here the length is not exactly the same. When I'm counting these walks, I'm counting walks that are shorter by one step. So if I want to have the, Okay, and here I'm making I'm counting, I'm taking hx as a bound for, walks that end up on this white line. So I'm largely overcounting, but in the end, if I just want to say that I can just restrict myself to prove that hx is finite. That if hx is finite, then gx is finite. So all this kind of thing will be fine. Okay, so then I have, well, the main case. So if I have a walk that starts from A, that goes either left or right, and then visits the half plane. So I have then two subcases. So the leftmost point is the last point, and two, the leftmost point is not the last point. Okay, so if the leftmost point is the last point, this means that I end up with either this step or this step. Because this step, or this step. Okay, because these are the only steps that kind of go left. Okay, so if I end up with, so this is kind of A, B, and C. If I am in case B, then what I'm seeing from the endpoint, well, it's just a half-plane walk. Okay, so just reversing the sense of the walk, I'm just saying, well, what I'm doing is just counting half-plane walks. Okay? And in case C and D, what I can say is if I just add one extra step in a deterministic manner, I will have an half space walk. So this gives me, and I'm not counting things, A and C. I can count them together, okay, because I don't need one hx for each of them. The only thing, so the correspondence is really one-to-one. The only thing I have to check is that if I'm counting this, I'm counting walks that have a length. I have augmented the length by 1. Okay, so I have to sum hx over x. Okay, so this is for B, and this is for C plus D, for A plus C. So far, so good? Okay. And now comes this part. So now, if the leftmost part is not the last point, then basically I have a step which is like this between two mid-edges, and then two things that okay. And this height can be visited several times. So I'm just looking at the first time things are visited. Okay, so this could eventually go there because I have nothing that tells me I don't know anything about the first step. Well, now if I have this, what I can do is do the same thing that I did for AT and BT. I'm saying, well, I can just look at the thing from there. I will encode my past until there by this red path, and the future until there by this blue path. Okay, these two things, they are half-plane walks, and if you take the sum of their lengths, you get the length of the orange path plus 1. So this gives you hx squared over x as a contribution. Okay, so I'm really grossly overcounting. There are lots of obstructions. Okay, when I have these pairs of paths, I mean, usually they are not usually, I mean, if you take two half-plane self-avoiding walks, I mean, if you take typically two of them, they will usually cross. So here I'm kind of overcounting because I'm only here. I have only pairs that are non-crossing, if you want. But okay, this is an upper bound. If I show that hx is finite, I'm done. Okay. So now, how do you control hx with bt? bt of x. So I have a half-plane walk. Okay, so what I can do is the following. I look at the maximum, the rightmost point that the walk has attained. Okay? And for the moment, I will assume that the rightmost point is not the last point. So this means that it has to be attained in a step like this. Okay? Your lattice looks like this. And basically, if the only way that you do not go right of your path right. Well, this is the only way you can get a rightmost point in the middle. Okay, so now I will look at really the last time I reach this point. Okay, so if I look at the last time I reach this point, so let's zoom in. I reach this, this abscissa. Okay. The last time the first coordinate is maximized. So yeah, so here, okay, there is a bit of a deal, but let's assume that the walk continues at least for 2 steps afterwards. So if the walk continues for 2 steps, then the only possible next step has to be this one. Okay, because if it continued this way, then it would reach this one, and this one would not be the last time you get to this maximal first coordinate. And then if you look at the future from this point, well, you know that you're never going back there. So in particular, okay, in particular, you don't know much more than this, but okay. Okay, so you know you're never going back there. So yes, so the idea is that now you can just play the same game and end up the walk at its rightmost point. Okay? And the idea is that, well, this thing from there, from this leftmost point, this gives you a bridge, okay? And then this procedure will give you another bridge, and then another bridge, and then another bridge. Okay, so there is a bit of issue. So here you see, basically, when you're constructing these bridges, if you have all the bridges, basically you can reconstruct the trajectory. The total length of the trajectory is not exactly the sum of the bridges because you're always taking away this step. Okay, so what you're doing to transform this, what you're doing to transform this part into a bridge is really, you just twist the last edge. So here you conserve the length, but you're really forgetting about this part. Okay, so you lose one in the length. And then you have many issues for what really, okay, for exactly what happens when things are ending. So this is what we are going to see now. So what happens when you end? So on your last bridge, okay, so I mean, basically, after you've done one step, you're kind of left off with something that looks very much like the starting point. So yes, so the important thing is that yeah, at your last step, you may end up with several ending schemes. So first possibility is that you end up with something like this. Just after your last visit, you end up with an edge which is like this. Okay? So in that case, what you're counting is, well, you exactly end up with a bridge. One possibility is that you just continue one step forward after that. So there are basically two ways to do it. So you can do either this or that. And then end up here. Okay, and well, if you do this, then you have no more bridges to build afterwards because this thing you have discarded it. So you have to count these options as well. And finally, there is this last way where you end up like this. Okay, but in this way, you have directly a bridge. So basically, there are two ways. There are ways where you are basically counting bridges, and there are two other possibilities where you don't really have a bridge. Yes, so okay. Let me write things down. So we want to bound hx. Okay? And what we say is that basically when I have my path, I can decompose it into a sequence of bridges. I name K the sequences of bridges. In the way I've done things, I'm sure that my sequence is finite because the widths of my bridges, they are strictly decreasing. Okay? Just because of this extra width 1 I'm gaining, okay, and because I'm staying in the half plane, I'm sure that the width of the blue thing, even if I go back there, okay, this will be smaller than the width of the orange thing, at least by an amount 1. So what I have is that T1 is larger than T2 is larger than Tk. Okay, and all my bridges, they have lengths larger than 1. Now the thing is that the last bridge, maybe it's not really a bridge. So one possibility is that it ends up either half a step, it ends up like a bridge. It ends up half a step after its maximum, or it ends up a step and a half after its maximum. So when you get a bridge, the contribution you get is really, well, the product over I equal 1 to k minus 1 x bti. The x comes from the fact that you're summing this extra edge here, so you get one more in length. Okay, and the bti is basically that you're summing over all bridges of length ti, and you completely ignore this constraint that these things have to avoid each other. When you sum over the last bridge, you get btk, but you get basically 2 btk for these two endings possibilities, 2x btk's for these two endings possibilities, and I think there is one more I forgot, which is this one. Okay, if you end up there, well, either you have to delete this edge or to extend your thing by one step in order to get a bridge. So, and I think it's safer to, basically you can end, I think if you put 3x here, you're fine. Okay, I think you can put either x or 1 over x here. This will be fine. Okay, so this is just saying, if you give me a collection of bridges, then I can almost reconstruct the walk. But basically, I have many possibilities in the way it could end, so I have to do a bit of surgery at the end. Okay? Well, the important part here is that when you look at this, okay, it looks a lot like an expansion. Okay, it's just an expansion, but there are a few terms that are missing. So what you can say is that this is smaller than, okay, you have 2 plus 3x over here. You can also divide by x, and here you have the product over t larger than 1 of 1 plus btx. Okay? If you expand this product, okay, and here you have an x. If you expand this product, okay, what you will get is exactly, okay. Well, you will choose 1 for most of the terms, and then for a few values of t's, you will choose this thing. So k here is just the number of values of t's that you have selected in your expansion. You can order them, and then for each of them you get a contribution x btx. Okay, except for the last one. So for the last one, I just put an x here and put this into factor. Okay, so I think the only source of mistakes that there can be is maybe this thing is not exactly 2 plus 3x, but yeah, basically you have to put something there because your work does not exactly end up like a bridge. And yes, and now if BT is summable, this is finite. Okay, so so the idea here is quite simple. Okay, you start from, you want to control the sum of all paths. Basically, you reduce to the case of half-plane walks by looking at the walk from its leftmost point. Okay, this is basically gives you this, and then you have to take into account all the other cases to make sure that you're not forgetting everything. Then once you have half-space walks, you just decompose them into bridges because what you have a control on is BT. And this allows you to control HX by this product, which you can show is finite. Okay, and yeah, I mean, basically, in the written references I've given you, I think they kind of omit the fact that you're losing one of length when you're doing this. And they don't care very much about the ending of the story, what's the fact that yeah, it's not clear for, I mean, the last bridge is not a bridge, and you have to do some surgery on it to complete it. But okay, it's not a big issue. So. Okay, so we are done with percolation and self-avoiding walks. We will okay, basically start from scratch again. The study of the Ising model. There will be some links to percolation that we will see, but it's largely independent. Okay, so there is an exercise sheet available on the web page. Okay, I hope it does not contain too many mistakes, but it's really a first draft. I have to add a few things, so maybe I will add a few hints. I mean, there are a couple of, I think, relatively easy questions, but most of the things are exercises that will basically get you thinking. So my advice is don't hesitate to think about it together. Write your solutions separately. This is all and yeah, don't be too worried if you can't solve anything. I mean, I think for this kind of class, everybody comes with a different background, and this exercise list, it's more, I think I will use it to evaluate and to give you a mark, but I think the important thing is more you to work on it in order to, well, kind of, well, have an opportunity to get back to what you learned during the class and use it and to basically reinforce your knowledge on percolation. Okay, so try to do your best, and this will be fine.